All right, so let's get started, my friends. There were two outstanding questions from the last class. One was about recycling photons, and I kind of emailed you about a legitimate answer to that question. About when we impose a beam in one of the paths, we impose a path difference element. It appears that the interference fringes or interference disappears, and both detectors start clicking. So what does that, how does that relate to the interference fringes? So I'm going to talk about this question today as well. However, before I get started with that particular question, I would like to shift gears a little bit and talk, instead of talking about the path of a photon, let's look at another degree of freedom of the photon. What could that be? Polarization. So let's start talking about an alternative degree of freedom, polarization. So let's talk about photon polarization. Now, when we talk about photon polarization, are we really talking about a qubit? Yes or no? Does the photon polarization represent a quantum state which is a qubit?
Yes.
Yes, it does. Yes?
Wasn't that related to spin out was one state and spin down was the other?
But that's one degree of freedom. You can have multiple degrees of freedom. So the path of a photon is also a qubit. The polarization of a photon is also a qubit. Why do we call it a qubit? Because bit means two levels and Q means quantum. So it's a quantum two-level system. So the polarization of a photon is also a qubit. So if you talk about the vector space in which this quantum state lives, what would be the dimensionality of this space? How many basis vectors would you have for a qubit? So how many basis vectors do you need? How many basis kets do you need to define an arbitrary quantum state of a qubit? So I have a quantum state psi. How many basis kets do I need to completely write down psi? 2, ket 0 and ket 1. These are two possible labels for those basis states. Ket 0 and ket 1 are the basis quantum states. And any quantum state, any vector, any ket that lives inside that quantum space can be expressed in terms of these two components with some coefficients A and B. And what are the constraints on these coefficients? Modular square sum is 1, and each one of them can be a complex number. All right. So for photon path, we've seen that if a photon takes a horizontal path versus it takes a vertical path, one of these states was labeled ket 0, the other state was labeled ket 1. So a photon, when we talk about its path, is a qubit, and it can be a workhorse in a quantum computer. Right now we're going to discuss the polarization of a photon. So what are the two physical states that represent the basis vectors for a photon polarization? Horizontal polarization and vertical polarization. That's one kind of choice of a basis. There could be other choices, but that's one possible choice. So let's call horizontal ket 0, vertical ket 1, because these are our labels. But in order to keep things a bit clearer, and for purposes that will come clear to you later, I would try to use a different labeling for polarization so that it's connected to the physical picture. So I will call a horizontally polarized photon ket H and a vertically polarized photon ket V. So any quantum state can be represented as a combination of ket H and ket V. You can write coefficients A and B here. All right, so H and V are different labels for the basis states, and I choose these labels because I want to differentiate from the path discussion. All right, so far so good. Now now if I have a normal beam splitter, what it does to the path of a photon comes in, here is my incoming photon, and there are two possibilities, either reflection or transmission with certain probabilities. If it's a 50-50 beam splitter, the probabilities turn out to be 1/2 each. All right, so this element is creating a superposition. Every element in a quantum computer or a quantum circuit does something to the quantum states. What this does is it creates a superposition. By the way, if this element is fed in with a superposition, it might create a basis state. That's what we've seen in the second beam splitter do in our quantum interferometer. It takes in two input paths. At the end, you get just one output channel. So every element in your interferometer does something to a quantum state. It might create a new quantum state. All right. So in this polarization picture, we can also have optical elements that do something to the polarization. So let me talk about one optical element, and let me just denote it by a rectangle. And let's call this a polarizing beam splitter. So it's more than a beam splitter. It does split the beams, but it's also aware to the polarization. All right. So it's also aware to the polarization. So what it does is, let's call this a PBS, a polarizing beam splitter. And what I'm talking about, a particular kind of a polarizing beam splitter. What it does is that light comes in, a photon, this light could be a single photon. It comes in, hits the polarizing beam splitter, and so this is one input channel. It only takes in one possible input kind of inputs, and there are two output channels, two possible output channels. One of them is a ket H channel, the other is a ket V channel. Could be in either orientation. So suppose the bottom channel is the ket H channel and the top channel is the ket V channel. So depending upon the polarization state of this photon emerges from either of the two channels, output channels. It can emerge into this path or it can emerge into this path. Very similar to a conventional beam splitter, but now the two output channels are aware to the polarization degree of freedom. So it splits out the beam, it creates two paths, but each path is tagged with a certain polarization. All right. So yes, यार अभी कुछ नहीं डाल रहे, कुछ भी डाल सकते हैं. Now this is our quantum state. Now let's look at certain examples. Now let's call this polarization beam splitter, let's denote it by P, and let's put in an HV. So it has two output channels, one corresponds to H, the other corresponds to ket V. And we can place detectors over here. Let's call this D1, D2, okay? Sorry, D2. Now a photon comes in. Let's look at certain examples. A photon comes in, state ket H. The photon is now in a state ket H. Which of these detectors is going to fire? D1 or D2? D1 is going to fire. The probability of click here is 1, the probability of click here is. This detector is not going to fire, which is another way of saying that if I take the input ket H and look at its overlap with this particular channel, which corresponds to a quantum state ket V, this overlap is 0. So the probability of detection here is 0. The probability of detection here is 1, because this probability of clicking corresponds to the inner product of ket H, which is our input state, with the ket corresponding to this channel. This is 1, all right? So if I input ket H, this detector is going to fire. If I input it ket V, this channel is going to fire. All right, so far so good. That's what a polarizing beam splitter really does. Now it's also possible that I create a superposition of ket H and ket V. I mentioned that this is a horizontally polarized photon, and remember we're talking about a single photon, just one photon. We're not talking about a kind of bath of photons. We're not washed by light. It's just a single, it's a very dim source of light, just one photon at a time. Could have vertical polarization, but we could have polarization in an arbitrary angle as well. We could have circular polarization as well. So each of these could be a complex number. So I could have states, for example, of this kind, ket H plus ket V with a factor of 1 over under root 2, ensuring normalization. So this is one possible quantum state, and this is the state of a single photon. Do not be misled by thinking that this represents one photon being in ket H and another photon being in ket V. This is just the state, the description of a single photon. Some people would like to say that if you ask someone what is a quantum state, it's a complete description of an object. So if just talking about the polarization, what I've written over here tells us everything that can be known about the polarization of the photon. Anyway, so this is one possible quantum state. It's a superposition of ket H and ket V, and just one photon. It's not a bunch of photons coming in, just one photon. It has a character both of ket H and ket V. So sometimes this can be represented by a new symbol, ket D. A superposition of quantum states, kets, is also a ket. It's a quantum state, and we can give this another kind of label as well, which is D. All right. We can also have ket H minus ket V. Just see the resemblance with ket 0 plus ket 1, ket 0 minus ket 1 is the same thing, just different labels. This is sometimes given the symbol A. D stands for diagonal, A stands for anti-diagonal, because in a diagonal polarization, the polarization is at 45 degrees with respect to horizontal. Okay? So if I were just to draw a cartoon, just a cartoon of the diagonal polarized state, this is what I could draw. This is an anti-diagonal quantum state. So these are just cartoonic representations of these states. Horizontal would mean this thing. Vertical would mean this thing. All right. So these are just cartoonic representations of the polarization. In fact, I could have ket H minus iota ket V, another possible quantum state. This is sometimes called the right polarized state. And if I were to draw this cartoonically, it means that the polarization degree of freedom rotates as the wave or the photon propagates. Everything is possible. And by the way, this is also possible in the classical world. Light has polarization and it can take various forms. You could also have ket H plus iota ket V. By the way, why am I putting ket 1 over 2 under root 2 with all of these states? For normalization, otherwise it won't make sense. But I could have other coefficients as well. I could have 1 over under root 3 here, say 2 over under root 3 square root here, 1 over 3 under root square root here, so on. So the normalization condition needs to be satisfied. In fact, I can have any quantum state that I choose, some kind of real number A, some real number B, some complex number. I can have arbitrarily arbitrary states, and they would represent polarization which is kind of elliptical. Anyway, so all of these are possible prescriptions of the quantum state. Now if in my polarizing beam splitter I have a ket V channel and a ket H output channel, my detectors D1 and D2, and I were to input a state ket D, which is this state, what's the probability that D1 clicks? Half. It's kind of ket D overlap with ket H modulus square, and I take in this description of D, put it in, use the orthogonality relationship between the basis vectors, I'll get 1 over under root 2 modulus square, which is 1/2. So the probability that this clicks is 1/2, and the probability here is also 1/2. And that's just one shot. Is it possible in a single shot to have two coincident clicks? No, because the photon cannot be split. It's a quantum. All right. So by the way, if you want to build up these probabilities, again, you have to repeat the experiment multiple number of times with multiple copies of identically prepared quantum states. Likewise, I can have ket A, I can have an arbitrary kind of configuration in which a state psi comes in suppose my psi is given by this state. So what's the probability that D1 clicks? What's the probability of this click? Half. If that's my quantum state, which I've written on number 2, what's this probability? A over 2, A squared, A modulus squared. The probability that D1 clicks is A modulus squared. The probability of D2 clicking is B modulus square, which by the way is 1 minus A modulus squared. Correct? All right, so far so good for polarization. So what we are really okay, now let's look at some aspects of measurement, quantum measurement through this basics that we've built. Some aspects of measurement and complementarity. What does a quantum measurement really mean? Right, so suppose I have a polarizing beam splitter PHV, two output channels, a ket H channel and a ket V channel, and I put a block here. And then I look at this channel alone. So I input a quantum state. If this quantum, so let's put a detector over here. Some D, let's call it D. Don't confuse D with diagonal. This is some detector D. Now a photon comes in, it will have some quantum state. If the quantum state of the photon, let's look at different scenarios. This is my psi in. Some photon coming in, psi in. I'm looking at the probability that D clicks. If my psi in were ket H, what this block does is that it's like an opacity. It's something that does not let the photon go out. All right. And this is all of this is in a box. And this is the opening in the box. And we are only letting a photon come out of this path. All right. And there's an input port, an input window, and an output window. A photon comes into this box. The internal construction of this box is as shown, and there's just one output port, and the photon comes out from this. A photon possibly comes out from this port. Now, if my input were ket H, what's the probability that detector D clicks? 0, because that photon will be steered to this path with certainty. probability 1. So this probability is 0. So nothing comes out here. So this is nothing. No click would be seen on D. If ket V is input, so what's this probability? 1. So that photon must come out of that output port and register itself on the detector. And if it comes out of the detector, if this comes out of the detector, what would be its quantum state? So if I were to measure the quantum state of this photon, or I would like to assign a quantum state to the outgoing photon, what would its quantum state be? What's the quantum state of this photon? Ket V. So ket V comes in and ket V goes out. So ket V is, we can write ket V is prepared. So this box, which is doing a measurement, has prepared a quantum state ket V, but interestingly, it's not a kind of very sophisticated preparation, because ket V was the state that was coming in the first place. But if this input quantum state were ket D, suppose the input quantum state were ket D, were a diagonal state, an equal superposition of ket H and ket V, in that case, what would be the probability that this detector clicks? 1/2. And in this case, if the detector doesn't click, there's no photon here, right? It's not that the photon is just annihilated, it just disappears, because it really has been blocked by this object, and it remains inside the box. You put in something, but you don't get anything out. It's been blocked. But if a photon were to come out, which has a probability of 1/2, then that photon is known to be in a new quantum state, which is ket V. So now you're inputting ket D, and now you have prepared ket V. So the act of measurement is preparing a new quantum state. So you are inputting one quantum state and you're getting at the output some other quantum state. So whenever you measure something, you can prepare new quantum states. The act of measurement generally prepares a new quantum state. The act of measurement in most cases is state preparation as well. Now if you were to take this arrangement, polarizing beam splitter HV, ket D comes in, you put a block here, you block this path, here you have created ket V. If this were to go into another PHV, which of these output channels are going to be populated? The top one or the bottom one? The top one, because with certainty this quantum state is going to land up here. D2 clicks and D1 does not click. This clicks and D2 clicks, because now you have prepared ket V and you have a polarizing beam splitter which separates out into the two channels ket H and ket V. Since you're inputting ket V, the output is going to be ket V. So there is no character of H inside this input. Had there been some ket H as part of this input superposition here, this detector would have clicked. So now what you've done is you have two polarizing beam splitters back to back. You prepare a new quantum state and you can verify that you have prepared this very quantum state by juxtaposing another polarizing beam splitter after this quantum state has been prepared, and with certainty, 100% probability that this detector is going to click. By the way, one question I would like to ask you: if I were just look at the two polarizing beam splitters in together, if I input a single photon, one photon into this system, this pair of, what's the probability, overall probability that you see a click here? 1/2. Because the probability that this path is taken is 1/2. The probability that with this path taken, the conditional probability is 1. So 1/2 into 1 is 1. 1/2. Yes, please.
Sir, you talked about preparing a new state, but both of उसके अंदर पहले से exist करती थी. So how is that preparing?
What do you mean? So
जब हमने cat D गुजारा तो cat D already had H and V.
right. So cat
exist करते थे.
करते थे, but now you have a new quantum state. Cat V is not the same as cat D. It has different properties. Now, do you get this point? Yes, please.
How would you verify that state V is prepared by finding?
Because this is
You won't know the probability of V1 is exactly 1.
so you need to do this experiment multiple number of times. All right. So now let's do something. So this cat V, the state that you've prepared here, it appears that it has no cat H component inside it. It does not harbor any cat H inside it. It has no H character inside it. I come to your questions, by the way, I remember. So now what we would like to do is let's try to modify this experiment a little bit. Remember that these are two identical polarizing beam splitters, but we can create other kinds of beam splitters as well. So if I were to take by extension a beam splitter which is dA, what a diagonal anti-diagonal beam splitter does, it's again another kind of polarizing beam splitter, is that it takes an input quantum state, some quantum state psi, and has two output channels. One is ket D and the other is ket A. That's it. There's nothing special about H or V. That's one basis, possible set of basis vectors. D and A is another basis. So any quantum state can be represented in terms of ket D and ket A as well. Now in order to kind of satisfy you for this, so if I have a two-dimensional flat space, nothing to quantum about it, Ex, Ey. Now if I were to take a point here, some point P, I can express this point P as some Xex plus Yey, right? So Ex and Ey form a basis to describe any point in this two-dimensional plane. But I can have any basis that I like. Any two orthogonal vectors, unit vectors, will form a basis, correct? So I can have an alternative basis. So I can have this set of yellow axes. I can call this a basis, correct? So let's call this vector Ed and let's call this vector Ea. Can I express the point P, which is a vector, in terms of Ed and Ea? Can I do that? Yes, of course the coefficients might change. Let's call this coefficient D and let's call this coefficient A. The coefficients might change, but the same point, the same vector can be expressed in another basis. So far so good. In fact, you can find out that if you knew X and Y, what would D and A look like? That would depend upon the relative angles between the two basis vectors and so on. So this is a nice exercise in basic mathematics. So there's nothing special about ket H and ket V. I can always decompose any, can I write this, for example, psi as a superposition of ket D and ket A with some kind of, let's call this alpha and beta. Alpha and beta are complex numbers. Can I write any quantum state in terms of ket D and ket A? Yes, I can do that. I think this would be one homework problem for you. All right. Any question about this? There are some kind of strange faces which means some questions, some inquiring minds. Yes, please.
But do DNA need to be orthogonal?
Yep. Otherwise, there has, for a unique decomposition, yes.
Sir, D and A are defined in terms of H and B. So how can we go from D and A, I mean from H and B?
This is your homework problem. Yes, please.
बीम स्प्लिटर की प्रोबेबिलिटीज पे सारे एक्सपेरिमेंट परफॉर्म कर रहे हैं. अभी हमने पिछले लेक्चर में गोडो प्लेटफॉर्म की बात की, तो हम एक्सपेरिमेंटली चेक कैसे कर सकते हैं कि बीम स्प्लिटर इज वर्किंग फाइन, वो बैड बीम स्प्लिटर.
Right, so how could you do that? So the question is, how do you know a beam splitter is working as it is intended to work? How will you answer this question? Any ideas? So you want to check whether this is, so I give you a beam splitter and I say it's a DA beam splitter. How can you verify that my claim is not ludicrous, that it is indeed a DA beam splitter? How can one check that in the laboratory? So you input known quantum states. You input known quantum states. You input a cat D. You prepare a cat D and see that this detector should never click and this detector always clicks. Right? You prepare cat A and see that this detector always clicks. You prepare cat H. You'll see that half of these detectors are going to click at one time. So you input known quantum states and check your element. Yes, please.
So why do we need a second beam splitter to make sure that the photon is coming out with get V in that diagram?
So how would you know otherwise? So this
we can simply place a detector after the first beam splitter, just we have
Here?
we have done in that diagram.
here, yes, we can do that. But if I were to yes, you can definitely do that, but the point is, it's going to come clear in this next picture, right? So if in this case, I would, in between these two beam splitters, place a third beam splitter. Of course, if I place a detector here, then the state cat V is created, but it's also possible that cat V is not created, cat D is created, because cat D is also going to give you a click. So just to be sure, so you can find out the probabilities as well. To have more certainty, it's good to let this pass through another. And if you're just doing an experiment with single photons and you just have one photon or a very few number of photons, how would you test that? You don't have the luxury of many photons. So you just put many identical beam splitters one after the other, and then you can be more sure. Okay, I have to go on, otherwise this is a never ending story. So now I have three beam splitters, PHV, the same scenario as we have over here. All right, and we know that this beam splitter creates a state cat V which does not have any H character in it. Just keep that in mind. This state, this state cat V does not have any H in it. Now what we would like to do is, so it's good to keep track of all the kind of distances. So here you go, a block here, this is my block. I put another beam splitter. Now this is a PDA. I have a block here. This is my D channel and this is my cat A channel. And then I put a third beam splitter, another HV beam splitter, and then I put two detectors here. This is cat H channel, this is my cat V channel, D1 detector, D2 detector. Alright, so this is my scheme. I know I already know that after this beam splitter I have created ket V because I have verified this to be ket V in a prior experiment. Now I take out this beam splitter, or in fact I don't take it out, I insert another beam splitter which is dA in between these two beam splitters. This has to be a dA beam splitter. It can't be a PHV beam splitter because PHVs don't help in making the argument. So I put in a PDA beam splitter and I put a block here. Is this detector now going to click? Can at the output, can you get a ket H photon? No or yes? Yes, you can. So even though this ket V did not have any ket H character, but once you pass it through this dA beam splitter and you block this path, and if a photon comes out here, then that photon has been created in a new quantum state, ket A. So you're taking an input ket V, and through this beam preparation box or state preparation box, you are creating a new quantum state, ket A. Now ket A has some H character in it, even though the input beam state did not have an H character in it. So this is a kind of a measurement, because if a photon comes out of this box, you know for sure with certainty, with certitude, that this is in the state ket A. So this is a beam preparation box. So you inputted ket V that did not have any H character in it, but through a state measurement or a state preparation box, you have created an altogether new quantum state that now does have a ket H component to it. And you can verify it because there is a finite probability that this detector is going to click. So this is the kind of argument that you really need to understand. This is a measurement box. Every measurement creates a new quantum state. All right, so if in this particular example, there is no uncertainty here in the H versus V manifold. There's no uncertainty. You're always getting a V state. There's no uncertainty. In this case, there is uncertainty. There is uncertainty, but you now know that the input state ket A is an equal superposition of H and V. How do you know this? Because ket A is really this state over here. The new state that you've created is a superposition of ket H and ket V. Therefore, if you pass this state through a polarizing beam splitter that discerns between H and V, you'll get equal probabilities that each of these detectors are going to click. And you can actually repeat this experiment with other degrees of freedom. For example, if you were to repeat this experiment with the spin of an electron, yes, the Stern-Gerlach. Subsequent measurements. Now what do you have in a Stern-Gerlach apparatus that splits up a beam of electron spins? Let me ask someone at the back, what do you have in a Stern-Gerlach apparatus that splits a beam of spins into two parts, say? Anyone at the back? Yes, please. Magnetic field of a special kind, inhomogeneous. So the magnetic field can be inhomogeneous and it can point in the z direction. That splits the beams in the z direction. If you just rotate your apparatus so that the inhomogeneous, so these are my two magnets. Suppose my hand are the two magnets, one magnet, north pole and south pole. This is magnetic field. What direction is the magnetic field in? Vertical or horizontal? Vertical. So let's call this a Z arrangement. I could also rotate this by 90 degrees. Now what's the direction of the magnetic field? Horizontal. Let's call the X arrangement. So if an incoming beam of electron spins is going to come into this configuration, the beam is going to split, might split, but in the horizontal direction. All right. So let's now kind of try to do these experiments. So first of all, I have a Stern-Gerlach oriented along Z. A magnet oriented along Z, two output channels. One is the beam going down. Let's call this ket minus Z, a beam going down, ket minus Z. And a beam going up, let's call it ket plus Z. I take some kind of orientation of the spin, any orientation of the spin, theta. Could be x, could be z, could be in between, anything. Or for kind of consistency, let's call it psi. Remember that when we talk about the electron spins, my ket psi can now be represented in the basis ket z plus minus z, AB. Ket z and ket minus z are now labels for my basis vectors. I can call this ket 0 and ket 1 as well. So the spin of an electron is also a qubit. The same language, the same Dirac notation describes different physical scenarios. One genotype, many phenotypes. Right? So it's one language that explaining different physical scenarios. Now this is an input quantum state, arbitrary, right? And I block this channel. So if electron spins come out of this channel, I put a detector here or somewhat, what will be the state of those spins? Ket z, of course ket z. If a spin comes out of this channel, it has to be in the state ket z, because any minus z coming out of this box has already been blocked, it's been obliterated, gone. Any spin that comes out must be in the state ket z. I have prepared ket z no matter what I input. Now if I were to put another Stern-Gerlach apparatus SGZ here and have two detectors, kind of D1 and D2, what's the probability that D1 clicks? 0. The probability that this clicks is 1 with respect to this. All right, so far so good. This is just analogous to this experiment. So all the electron spins that are coming out, one electron spin comes in, no matter what its state is. Here you have prepared ket z, so only ket z spins can come out of here, nothing comes out of here. All right. So you have prepared ket z and then you can verify it with this apparatus. So we have two Stern-Gerlach apparatuses back to back. Now let's modify this a little bit. I want to draw the analog to this. Do you understand analogs? The kind of similar thing to this. And for that I would draw a Stern-Gerlach apparatus along Z, followed by a Stern-Gerlach apparatus along X, followed by another Stern-Gerlach apparatus along Z. So an electron spin comes in, there's a block here, arbitrary input quantum state, this goes here. So I know that I have created ket z here, but now this ket z input is fed into an oriented Stern-Gerlach apparatus. I also place a block here, by the way. So this Gerlach apparatus has two output channels. One corresponds to minus ket x, the other corresponds to plus ket x. One is right, the other is left. I block this path, and then I have at the end the ultimate Stern-Gerlach apparatus is another SGZ with two detectors, D1, D2. Now this beam is fed in here. What's the probability that each of these detectors is going to click with respect to this? 1/2 each. All right, 1/2 each. So even though, which means that in some cases I will get a ket minus z electron spin, even though I have kind of blocked all minus z ket minus z spins here, because this box is now creating a new quantum state, which is ket plus x, and ket plus x has in fact an equal superposition of ket z and minus z. All right, so before I take your questions, one small exercise for you. Just as a simple exercise, by the way, you'll be asked in your quizzes and your exams to calculate these probabilities. All right, this is the fun part. Can you express ket h as a superposition of ket d and ket a? Can I do that? So what would be the coefficients? So look at these definitions that we have over here, d and a. If I want to express ket h as a superposition of d and a, what would be the coefficients here look like? What would they be? What should I write over here and here? Sorry? Bolo? 1/2 for each? Yes. You can verify this. So any quantum state can be represented in any basis that we choose. Yes, please, there was a question. What is? This thing?
Why was the thing coming out as plus x instead of
So, right, so this is a Stern-Gerlach apparatus. It has two output channels. So the output channels correspond to certain kets, certain quantum states. So a Stern-Gerlach apparatus, which is a magnet which is oriented vertically, will produce a beam that is vertically split. So one of the output channels is, let's call it pointing the plus z, the spin is up, the other is spin down. This is an oriented Stern-Gerlach. So one channel corresponds to spin in this direction, the other corresponds to spin in this direction. Because in this new basis, this is up and this is down. In the vertical basis, this is up and this is down. Got it? So this is also something, the main measurement idea is that each measurement creates a new quantum state. And it's really not possible. So another corollary of this, yes, very important point. Another corollary of this is that objects do not have fixed properties. Because, baat suno beta, a quantum object is very hard to say whether it is horizontally or vertically polarized. A horizontally polarized photon has some character of diagonal polarization in it, an anti-diagonal polarization in it. In fact, a horizontally polarized photon can also be written as a superposition of left and right circular polarization with some coefficients, which is your homework problem, homework number 2. So it's really hard to say. It's not kind of nice to ask the question, what is the polarization of a photon? It's not nice to ask the question, what color are your eyes? If your eyes are a quantum object, it doesn't make sense what color they are. It's kind of strange to ask this question because there's no intrinsic property of horizontality or verticality when it comes to the polarization of a photon, or the orientation of a spin when it comes to the spin of an electron, or the path a photon takes when we're talking about the path degree of freedom, and so on. So these properties lose their objectivity, and it's all important in what context are we studying them. Quantum mechanics is really contextual, and this is in fact a philosophical concept, contextuality. Contextuality. So quantum physics puts the observer back at the center stage. पहले जो न्यूटन साहब थे उन्होंने कहा यार observer doesn't matter. It doesn't matter which country you're looking at an experiment. It doesn't matter who is looking at the experiment. But quantum physics really brings back the measurement process and the context in which you're making a measurement and the kind of measurement you're making. It makes it center stage. So the measurement is central to quantum physics. Now after the lecture, after the break, which is going to be a 10-minute break, I'm going to talk about quantum erasure, and I'm going to come back to some earlier questions. Quantum erasure is really quite an interesting and a very weird phenomenon that quantum mechanics and physics allows us to investigate. So let's take a 10-minute break. All right, so question, I would like to start off with the question. I'm talking about the spin of an electron, and I want to create a spin which is oriented along the x direction. What do I do? Block. So I want to create this quantum state ket x, which is spin pointing in this kind of direction. What do I do?
Pass it through a SDX apparatus and then block off the SC minus X.
Exactly.
Get minus X.
Right. So I take any input quantum state, any spin, it has to be a spin, right? I take an electron which has spin, of course it has spin, and I pass it through a Stern-Gerlach apparatus oriented along x minus x like this, and I block the all right, I block the minus x channel. This channel I block, and I let the spin go out through this channel. So this, if a spin comes out of this channel, which I can detect, of course, because I have some detectors. For example, I can put a photographic plate here. And a blob appears here. It means that spin that has come and hit this point must be in the ket x direction. All right, got it? So this is how, if I remove this photographic plate, now whenever I have a spin coming in, I put this into another experimental apparatus, I know that the incoming spins would be in the state ket x. This is how I prepare states. One way of preparing states. By the way, if I were to input ket x, I would have no losses. I will always get that spin coming out. Okay? If I input ket minus x, I never get a spin out of this, because ket x and minus x, they are orthogonal states. X and minus x, they are orthogonal. First of all, do you know ket x and minus x are orthogonal states? Right. So if I input ket minus x, there's no probability for it to go take this path. So I will never get a spin here. Right? If my spin is in an arbitrary direction, say theta, with some combination of ket x and minus x, what's the probability that I will get a spin here? 1/2? Nope. Some theta, depends upon theta. Yes, please. Can you please first answer my question? Yeah, there is some ket theta. Suppose my input quantum state my ket theta is some cosine of theta ket x, let's call it so this is my definition of ket theta. All right, is this a normalized quantum state?
Yes.
Is this a quantum state? Are ket x and minus x the two basis vectors? So one thing you must keep in mind is we talk about quantum objects. Ket x is spin pointing the x direction, ket minus x is spin pointing in the opposite direction. In physical Euclidean space, they are not orthogonal vectors. Keep that in mind. They are kind of anti-parallel vectors, but we're talking about quantum space. We're not talking about the physical Euclidean flat space. So in the quantum space, in the Hilbert space, this is one ket and this is the other ket. Spin up and spin down are orthogonal quantum states. We're talking about quantum states here. This is quantum physics we're learning, right? So these two quantum states, ket x and minus x, are indeed a basis for the spin degree of freedom. And this is how I have defined ket. This is normalized quantum state. So if I were to input this quantum state into this oriented Stern-Gerlach apparatus, what's the probability that a detector here is going to fire? Cos square theta. Because it's going to be ket theta overlap with ket x in a product modulus square. So this is just this term squared. Right, got it? So another way, if we were to move back to the polarization degree of freedom, I've shown you a device called a polarizer, which is a kind of an object or film which has an optic axis. If my polarizer, I'm going to use pink for polarizers. These are optical devices. So this polarizer has its optic axis along the horizontal direction. And suppose a photon comes in which is ket h. What's the probability that if I were to place a detector here, that this detector is going to click? 1. If the input were ket v, 0. If the input were some cosine theta ket h plus sine theta ket v, what would this be? Cosine square theta, and so on. So if this angle were say different, say some alpha, I need to find the relative orientation between the axes, or I can, all right. So this is another homework problem. Okay. All right, so far so good. So now let's look at a really confounding experiment which we can do in the lab. I can show you some results today which are experimental results, and this is the concept of a quantum erasure or the phenomenon of quantum erasure, and it's also linked with the idea of delayed choice. So quantum physics has some popular buzz appeal as well, right? So it attracts youngsters. If they move away a little bit from Facebook and the social media stuff and they kind of look at what's going on in the world, it has an attractive magnetic personality. And one of the ideas is this delayed choice experiment, just as entanglement and so on. So delayed choice, the gist of it is, if I were to use popular language, you can change the facts of the past. What happened in the past can be altered. Now what does that mean? let's try to get into this. So if I come back to my Mach-Zehnder interferometer, so for kind of, let me just erase this part. We've already seen what a Mach-Zehnder interferometer is, a 50-50 beam splitter. Another 50-50 beam splitter. Sorry. Two mirrors and two detectors, D1 and D2. Now I'm back to the polarization degree of, back to the path degree of freedom of a single photon. A photon comes in, this path gets 0. We've noticed that if we set the interferometer arm lengths properly, perfectly balanced, perfectly matched, both of these arm lengths are perfectly the same, or kind of in multiples of some wavelength, then only this detector is going to click. PD1 is 1 and PD2 is 0. And we say that this corresponds to interference because we don't know which path that single photon has taken. We do not have the which path information, but we do have information about the momentum. Now what we did in the next process was the following. So this is so far so good. So in the next stage we moved on, built up our description. Now let's have a beam splitter. D1, D2. Now if I were to put a kind of path element or a phase element here, phi, and I had a single photon coming in, I can control these outcome probabilities, and we did a calculation of state progression. So this probability PD1 is, for example, given by cosine square phi by 2, and probability D2 is given by sine square phi by 2. For certain values of phi, 0 and pi, only this detector clicks. For phi equals pi, this detector clicks, and for in between phi equals say pi by 2, both of these detectors are going to click with equal probability. Now your question about when both of these detectors are going to click, the momentum is uncertain, but the path also remains uncertain, and that's allowed, and that does not violate the uncertainty principle. And in order to explain this fully, I have to describe this in terms of block spheres and block vectors. But it's possible that both the path and the momentum remain uncertain. Okay. Now we've seen this. So what this beam splitter does, it introduces a phase difference between these paths, and that phase difference is then captured in these probabilities. Now is it possible? It's also possible to not have this phase path and change the distance or displace this mirror a little bit. So what this beam splitter does, light comes in, it slows down a little bit, it takes longer to travel inside the glass element, it does more cycles inside the glass element, the phase changes, and then the two waves here, which are subcomponents of a single wave, they recombine constructively or destructively on either channel. It's also possible to achieve the same effect as you would do in a normal interferometry experiment by removing this object and changing the displacement of this mirror. That's what happens, for example, in a Michelson interferometer that you would normally have in the laboratory. So I can do a version of this experiment in the following fashion. So this is just my placeholder for drawing the diagram. A beam splitter, mirror, fixed mirror, beam splitter, fixed beam splitter, and now I have a mirror whose position can change through some distance d. So I can move it up and down. For example, if this mirror were to move up a little bit, then one of these paths is going to change its length. Therefore, the probability of detection at each of these detectors might change. So you can achieve the same effect as you've done with this phase element by displacement of this mirror. So why do we get interference? We get interference because of the difference in path lengths. So you can achieve the same effect by displacing one of the mirrors. That's so far so good. So the probability that each detector clicks might change, will change if this path length changes. So if I were to make a plot between the displacement d and the probability that d1 clicks, this probability is going to vary as a cosine square function with respect to d, with respect to some factor of d and the wavelength of the photon. All right. So I can achieve the same effect as I achieve with the phase element by displacing this mirror. So this looks like interference fringes. Okay. By the way, so I'm getting a little bit into experiments. This is what you would do in a Michelson interferometer. You might have worked with a Michelson interferometer in school. You have two path lengths and you change one mirror little bit and you get a different kind of interference fringe. Anyway, this is a nominal beam splitter. It achieves the same effect as you would do with a phase element, because this d also imparts an extra phase element, which by the way is given by EI k kd, where k is 2 pi over lambda d. So this is just like EI phi. Okay, kz is the phase, k is the wave vector, and that is equal to 2 pi over lambda. Lambda is the wavelength of the photon. So EI phi, which you achieve with this element, can also achieved by a displacement, and I've shown this mathematically here. It's also possible in real experiments, by the way, when we perform this experiment in the laboratory, we have our beam splitter, mirror, fixed mirror, beam splitter, and instead of a detector, we can place a screen over here or a camera. And since light, a photon, it's a beam of photons, it has a finite size. It has a finite size. You cannot have a pencil sharp beam. That is against the laws of optics. It has a finite size and it also spreads out a little bit. It diverges. Therefore, if you put a screen here, you would actually see interference fringes. On this channel, which indicate the interference is taking place. Now this is an experimental kind of technical detail, and this is how you prove that interference happens in the lab or not. Anyway, let's move back to our ideal scenarios of detectors. All right. So we're trying to build up the argument for quantum erasure. Argument number 1, step number 2, step number 3, step number 4. Yes, please. तब भी आएंगी, लेकिन then the analysis becomes complicated. All right, look at step number 1. You have to pay attention to this. This is subtle, kind of complicated, but beautifully satisfying. Number 1, marks and interferometer. Only D1 clicks. Interference, yes. Certainty in momentum, yes. Uncertainty in path. We don't know which path the photon takes. Right? There is no mechanism to see if a photon comes out of this path. We do not have any mechanism, any technique to determine which path the photon has taken. We can mess up with the experiment and put detectors here, but then we will not see an interference fringe as we saw in the bomb experiment. All right. However, now let's kind of put polarization into this picture as well. Now in this arrangement, this is my cat 0. Now this experimental arrangement does not care about polarization. Got it? Because there is no element that deals with polarization. So it's oblivious of polarization. Polarization is not a relevant degree of freedom in this setup. However, if I were to introduce polarization into this setup, and I make this photon polarized. So now let's make this photon diagonally polarized. So photon comes in the path ket 0, but it's also diagonally polarized. All right. So now what degrees of freedom are of my interest now? Both path and polarization. Now I want to represent this quantum mechanically. So how do I normally do this? Is now I have 2 degrees of freedom, both path and polarization. So I would write down the quantum state, which is now, it's called a composite quantum system, because it involves both the path and the polarization. So what is the path? What state is as far as path is concerned? Ket 0. What state is as far as the polarization is concerned? Ket D, which I can also write as right. So this is the polarization part, this is the path part. This is one quantum degree of freedom, this is the other quantum. The overall quantum system has both of these degrees of freedom. So generally, notation wise, I can put this symbol in between these 2 degrees of freedom. Just notation, this just notation. All right. So this is called, you can call it O cross or a direct product, O cross. Let's call it O cross or times or cross, whatever you would like to call it. So this is now our input quantum state, which has a path degree of freedom and a polarization degree of freedom. Now here the photon comes in, this has been designated ket 0, ket 1, the mirror converts this to ket 1, it converts this to ket 0, everything then recombines here, and here you will get an output state on ket 0, right, because this is the ket 0 path. But what happens to the polarization? Nothing. The polarization is not affected. We are assuming that none of these elements is altering the polarization. The polarization, this is not a polarizing beam splitter, this is just a beam splitter, this is just a mirror. And we are assuming that none of these elements changes the polarization whatsoever. So the output state is also going to be ket 0 plus the original polarization that you input. This is the quantum state of the photon here. It does not have a ket1 component, so this channel is not populated, this detector is not going to fire. This is my output. In the state progression, we've done all of this part. 0 goes to a superposition, then it recombines, and then you get this as the output. But I'm just tagging along, dum challe ki tarah. I'm just tagging along the polarization part with it, just attaching it for completeness sake for the next arguments that I'm going to build. We know the momentum of the outgoing photon, but we don't know the path. It's in a superposition. Now, is there a way to kind of determine the path? Let's see. All right. So in this experimental arrangement, let's do another kind of trick. Let's put a polarizer here which is horizontally polarized. Correct? Pink represents polarizers. And let's put a polarizer here which is vertically polarized. This is my step 5. Now the quantum state that comes out is this particular quantum state. Now does the photon take this path? Never. Because the path is just defined by ket 0. So it must take this path. Now this photon is diagonally polarized. If a photon reaches the detector, ultimately, what is its polarization going to be? Ket H. So in half of the cases, a photon will not be detected. If a photon comes out of this path, by the way, a photon going in must always come out of here. It's not kind of blocked anywhere. But in half of the cases, that photon will not be able to reach the detector because of the orientation of this polarizer. So if I were to put a polarizer, a horizontal polarizer here, the output is going to collapse. So we input diagonal with the polarization. The polarizer does something to this polarization. It just outputs ket H. If a photon comes out, it must be horizontally polarized. So it takes this diagonal polarization and prepares a H polarized photon. It collapses this superposition into ket H. And your final quantum state of the photon that reaches the detector is ket 0 crossed with ket H. It's in the 0 path, horizontally polarized. And you will never, by the way, see a photon here. You will always see, if you were to see a photon, which happens half of the times, it's going to be always on this detector. Now, there is interference because only one detector clicks. We know the momentum, but we are uncertain about which path the photon has taken. Uncertainty principle holds good, so far so good. But we've added these polarizers at the output channel. Yes, please.
Sir, incident क्या था और हमें अब मिला क्या polarization के बाद? So incident was the diagonal one, लेकिन इधर तो ket 0 लिखा हुआ है.
किधर ये?
Yes.
This is path,
Oh, no,
but this is polarization, diagonal.
okay, लेकिन उधर क्या हो रहा है? Like
इधर ये मिल रहा है.
ये तो पहले भी था.
ठीक है, आने दो.
ठीक है.
ठीक है.
So preparation किधर हुई है?
अभी नहीं हुई. अभी इसमें से इसको कोलैप्स कर दिया, डायगोनल में से सिर्फ हॉरिजॉन्टल मिल गया यहाँ पे, क्योंकि ये पोलराइजर है. ऑल राइट, सो नाउ लेट्स लुक एट अ वेरिएंट ऑफ दिस एक्सपेरिमेंट. लेट मी मूव ऑन. जी, वन लास्ट क्वेश्चन.
Why probability that D1 clicks in this case is 1/2? Why not 1?
Because this is my polarization, input polarization into this polarizer. I take the overlap of this state with ket h. So it's 1 over under root 2 square, 1/2. All right. Number 6. Now I have the same Alexander interferometer. Please pay attention. So this is number 5 redrawn. Yes. ठीक है. Now I would like to do a twist. I input a photon in the state ket 0 crossed with the diagonal state. This is my input, and now inside the interferometer, inside it, I place polarizers. I place a polarizer here which is horizontal, and I place a polarizer here which is vertical, and I have two paths. One path is labeled 1, this is path 1, the other path is labeled 2. Now quantum mechanically, quantum physically, which of these detectors is going to click? Think in terms of the uncertainty principle. I give you 2 or 3 minutes to think about it. Don't speak out the answer, just think about this. Take your time, 2-3 minutes. Be in a pensive mood, think, reflect, and see which of these detectors is going to click. Think in terms of the uncertainty principle. Path and momentum complementarity. One photon is shot in, only one. One photon is detected. Only one of the two detectors is going to be detected, is going to fire. So can anyone raise his or her hand and kind of give me an answer to this? Someone from the back. Yes, please. Which means, what about which detector is going to click? Which means either of the detectors is going to click. What's the probability that D1 clicks? 1/2. And what's the probability that D2 clicks? 1/2. So we have complete uncertainty in the momentum, which means we must know the path of the photon. Now if a photon is detected, now let's enter a Socratic dialogue. One photon is detected. How many detectors fire? One. Can we tell which detector fires? Beforehand we cannot, but once we've done an experiment, we know which detector fires. It's D1 or D2. If D1 fires, does a photon hit D1? Yes. If D1 fires, a photon hits D1, do we know the polarization of that photon that has hit D1? Yes. So if D1 fires, we know it must be horizontally polarized. Now a horizontally polarized photon is coming in. So we have now broken the distinction between horizontal and vertical. So that horizontal photon, which of these paths must a horizontal photon take? Can a horizontal photon take? Path number 1. So now if D1 clicks, we know that that photon that has produced that click. So if this detector fires, we know that this photon has come out from path number 1. We have information about the path. And we have information about the path because we know that this photon must be horizontally polarized by virtue of this polarizer here. So if this detector D1 clicks, the photon must be horizontally polarized. And if it's horizontally polarized, only a horizontally polarized photon must take path 1 because it is blocked inside path 2. Because this vertically oriented polarizer does not let a horizontal polarized photon pass through. So it must have come through this path. So now we have information about the path. We must be uncertain about which detector clicks. So even though by looking at the clicks, each click we can determine which path the photon has taken. So we have which path information. So with this path of the photon, it was equally likely that this detector may have clicked. So by looking at the clicks, we can determine the which path information, which means that we're totally uncertain about which detector has clicked. D1 may have clicked, D2 may have clicked. If D1 clicks, we know it were a horizontally polarized photon. If D2 clicked, we know it were a vertically polarized photon. If D1 clicked, we knew it must have taken one path. If D2 clicked, we knew it must have taken the orthogonal path. So we now have obtained which path information is available. So which path information has become available? Interference disappears. Only interference disappears. If we were to put a screen over here, we would never see fringes. I'm coming to this point 4. If we were to replace this detector with a screen, we would never see fringes. If these polarizers were absent, we would see fringes. So if which path information is available, we're uncertain about the momentum. So there is this complementarity between path and momentum. Let's do a quantum state progression for this. And I think it's a nice exercise. It's very easy to follow, it's actually fun. So this is my input state. What the beam splitter does is creates a superposition of paths. So let's look at the quantum state before the kind of polarizers. So ket 0 goes to 0 plus 1. So I normalize each. So these are called subspaces. This is one subspace, this is another quantum subspace. These are two quantum subspaces. And I am making a composite system with two subspaces, one of the path, one of the polarization. Alright? And remember, this is just rotation. Don't be afraid of this rotation. So this beam splitter creates this superposition, does nothing to the polarization. So for shorthand, I just write this as ket B. Or let's spell it out. Now what the two mirrors do, they just interchange 0 and 1. So I just leave it, I don't add the action of the mirrors. Just they interchange, but that doesn't make any difference. But what does this polarizer do? Here a state, it collapses the polarization. So any kind of photon that takes this path, which is the ket 0 path, let's call it the ket 0 path, must be horizontally polarized. So this polarizer is actually doing a freedom. It's actually doing a collapse in the manner which we showed the polarizer. So what this polarizer is going to do is that it's going to connect ket 0 with ket H. Ket 0 with ket H. So any photon that takes this path, which is the ket 0 path, must be horizontally polarized. Ket 0 is now unconnected with ket V. We have collapsed this quantum state, this overall quantum state, into a new quantum state, but we still have a superposition of this kind of correlation plus ket 1 being vertically polarized. And I need this for normalization. This is my new quantum state after I've seen the two polarizers. In fact, I've missed a number of steps. You could do this step by step. Let's do this as a homework. Find the action of this polarizer. This polarizer projects 0 is connected to ket H. In fact, you might be easier if you were to place this polarizer over here, right? That might make things easier for you. So let me just, it doesn't make any difference whatsoever, but for calculation this might be easier for you. All right, we know the action of the beam splitters, we know the action of the mirrors, they interconvert ket 0 and 1. Finally, you're left with a state of this kind. So let me do the complete calculation, by the way. So this is my arrangement. Please be patient. This is my state over here. What would the two mirrors do? Mirror 1, mirror 2. This just converts ket 0 to ket 1, ket 1 to ket 0. Got it? That's it. So nothing happens. And then H plus V. Now let me split this up. Let me expand this. 1/2 ket 0 O cross H plus ket 0 O cross V plus ket 1 O cross H plus ket 1 O cross V. Got it? I've just expanded the dot product. It's linear operation. Is this state normalized? Yes, it is. It's square of this is 1/4. 4 times gives me 1. So now what the polarizers do? So now I add the polarizers in the respective paths. What happens to this state? This is now my ket 0 here. This is my ket 0. This is my ket 1 because horizontal path is ket 0. This is the vertical path. Horizontal path is ket 0. This must be tagged with vertical polarization. So ket 0 and this thing disappears. It's blocked. Likewise, this is ket 0 here. Horizontal path we've taken to be ket 0. This is ket 0. It's vertically polarized. It must be vertically polarized. So ket 0 with H annihilates. It goes away. Likewise, ket 1 must be horizontal. So this goes away. So I'm blocking half of these probability amplitudes, half of the terms. That's what the polarizer does. It just doesn't let this pass through. This state does not propagate. It's blocked. Likewise, this state is blocked. Got it? Now what I could do, I could write the overall state as ket 0 O cross V plus ket 1 O cross H. Now I want to normalize this, so I put 1 over under root 2. I normalize this again. I want to keep things normalized at every point. Yeah, any confusion? Konsa? This is not equal to. This is what the state propagates to. So when you have some part going away, it's a loss. So loss measurement cannot be represented in this fashion that you just keep all the coefficients preserved. Every state has to be normalized. So this is our new quantum state. So what happens at the second beam splitter? Let's see what happens at the second beam splitter. Please be patient. Let's finish this off. Let's finish this off. What happens to ket 0? By the way, this state is called an entangled quantum state. This is an example of an entangled quantum state between the entanglement between path and polarization. This is your first kind of acquaintance with an entangled quantum state. I'll explain this later, but so ket 0 goes into a superposition. So this state over here, let's expand this state. Let's expand this. Can you help me please? 1/2 0 cross V plus 1 crossed with V plus 0 H. Is this normalized? Yes, it is because of this factor. Now this is the quantum state before the two polarizers at the output. This is the output quantum state. Now this sees two polarizers at each of the two channels. This is my output channel ket 0. This is my output channel ket 1. So in the output channel ket 0, the photon, if it were to exist, would see a horizontal beam splitter. So ket 0 cannot be tied up with ket V. This is blocked. Ket 1 with H is going to be blocked. So we left with, now I'm not putting an equal to sign here. This is after the action of the final polarizers. And I'll put the coefficient later. 1 crossed with V plus 0 crossed with H. The 1 over under root 2 must be the normalization factor. Which means if, now when I do a measurement, when a detector clicks, any of these terms is gonna click, is going to produce a result, which means collapse is going to take place. Projection is going to take place. The two possible output channels are ket 0 and ket 1. So if D1 clicks, then I have really created the state ket 0 crossed H, which means I have detected a horizontally polarized photon along the channel ket 0. If detector D2 clicks, I have created the state ket 1, ket V, before which is now kind of eliminated because of the detection process. But this, if the detector D2 clicks, it must have corresponded to a vertically polarized photon. This again is an example of an entangled state. So now the intuitive reasoning that either of these detectors is going to click with a probability of 50% makes sense. And now I know, depending upon which detector clicks, which path has the photon taken. So far I haven't described quantum erasure, by the way.